Bismillahirrahmanirrahim. My name is Khadija and my ID is 9. I am the student of BS Chemistry and my source person is Dr. Hammad Majeed. My topic is about concave lens. First, we know about the history of concave lens. The history of lenses dates ancient times. The ancient Egyptians used simple magnifying lenses made of crystal to enhance their vision. In the 13th century, the scholar Roger Bacon studied the properties of lenses and wrote about their ability to magnifying objects. During the Renaissance, advancements in lenses making occupied in Europe. In the 17th century, Antony van Leeuwenhoek crafted high-quality microscopes using small, powerful lenses, leading to significant discoveries in microbiology. The 18th century saw the development of achromatic lenses by opticians like John Dolland, which reduced chromatic aberration. In the 19th century, lens manufacturing techniques improved further with the introduction of precision grinding and polishing. The field of optics expanded significantly in the 20th century with the advent of new materials and coating, enabling the creation of complex lenses designed for camera, microscopes, and telescopes. Today, lenses play a crucial role in various optical instruments and imaging technologies, contributing to fields ranging from astronomy to medicine and photography. Introduction of lenses. A lens is any transparent material having two surfaces of which at least one is curved. Lenses refract light in such a way that an image of the object is formed. Transparent. What is transparent? A material allowing light to pass through so that objects behind can be seen. For example, a transparent blue water. Types of lenses. Lenses of many different types are used in optical devices such as camera, eyeglasses, microscopes, telescopes, and projectors, etc. But two main types of lenses are concave lens and convex lens. Convex lens, the lens which causes incident parallel ray to converge at a point, is called convex lens. It is also known as converging lens. This lens is thicker at the center but thin at the edges. Types of convex lens: plano convex, double convex, concavo convex. Concave lens, the lens which causes the parallel rays to diverge from a point. This is called concave lens. This lens is also known as diverging lens. This lens is thin at the center and thick at the edges. Type of concave lens: double concave, plano concave, and convexo concave. Concave lens model. With concave lenses, three simple rays can again be used to show the location of an image. The first ray is once again the one that passes straight through the center of the lens. This rays would get refracted one way upon entering the lens and then refracted equal the other way upon exiting the lens. With the thin lens assumption, this is equivalent to a straight line passing through the center of the lens without any refraction lens parallel to the optical axis. Since concave lens diverge light, this ray does not get refracted to pass through the focal point, but rather so that its imaginary continuation passes through the focal point on the same side of the lens as the object. The object's distance from the lens. The distance between both the image and the object from the lens can once again be expressed by the thin lens equation. 1/f is equal to 1/, distance of object plus 1/, distance of image. This time, looking at the thin lens equation, it is noted that with the negative value for f for a concave lens, di will have to be negative, indicating the image is a virtual image. This stands true for all value of do, which is always positive by convention. Magnification. One aspect of real and virtual image is that the thin lens equation does not calculate is the image size with respect to the size of the object. One of the most powerful uses of lenses is not just to reconstruct images of objects but to magnify those images as well. The magnification of an image can be calculated by m is equal to hi over ho is equal to minus di over do. M is equal to h prime over h is equal to d over f. do जो है डिस्टेंस of the object at the center of the thin lens. Di distance of image. F is the distance of the image formed from the center of the thin lens, where m is the magnification. Ho is the height of the object and hi is the height of the image. Lens terminology. Medium, an object through which a wave passes, in this case light. This could be air, glass, water, etc. Refraction, the phenomena of lens changing the direction in which light rays travel. Optical axis, an imaginary line that passes through the center of the image, through a center of a lens perpendicular to the lens surface. It is also called principal axis. Collimated rays, light rays that travel parallel to the optical axis of a lens focal point. The point marking the focal length on the optical axis, it is also called principal focus. Lens power, the reciprocal of the focal length of a given lens. Focal length, the length from the center of a lens to be point on the optical axis through which all collimated light rays refracted. Medium, the medium of a lens refer to the material through which light passes. Common lens medium, including glass and plastic. To find the power of a lens in a medium, we can use the following formula. Power of the lens is equal to the refractive index of any medium other than air, which is divided by its focal length. P is equal to n over f. Refraction, when the light rays is passing from air into a more denser medium. Since the light rays is passing from the medium in which it travels relatively fast into a medium in which it travels relatively slow, it will bend towards the normal line. This is the SFA principle of refraction. When the light rays is passing from a medium in which it travels relatively slow to a medium in which it travels fast, it will bend away from the normal line. This is the SFA principle of refraction. Now let's investigate the refraction of light by double concave lens. Suppose that several rays of light approach the lens, and suppose that these rays of light are traveling parallel to the principal axis. Upon reaching the front face of the lens, each ray of light will refract towards the normal to the surface. At this boundary, the light ray is passing from air into a more denser medium. Since the light ray is passing from a medium in which it travels relatively fast into a medium in which it travels relatively slow, it will bend towards the normal line. This is the FST principle of refraction. Once the light rays refract across the boundary and enters the lens, it travels in a straight line until it reaches the back face of the lens. At this boundary, each ray of light will refract away from the normal to the surface. Since the light ray is passing from a medium in which it travels relatively slow to a medium in which it travels fast, it will bend away from the normal line. This is the SFA principle of refraction. Refraction rules for a diverging lens. Any incident ray traveling parallel to the principal axis of a diverging lens will refract through the lens and travel in line with the focal point. Any incident ray traveling towards the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis lens and travel parallel to the principal axis. Optical axis, the straight line joining the pole and the center of curvature of the lens is extended on both sides. It is called optical axis. The optical axis is also called the principal axis. This principal axis is taken as x-axis. The height measured upward and perpendicular to the principal axis are taken as positive, and the heights measured downward and perpendicular to the principal axis are taken as negative. Collimated rays. A collimated beam refers to a beam of light or other electromagnetic radiations that is parallel and uniform with minimal divergence or spreading as they travel. In similar terms, it is a beam of light that maintains its size and shape over long distance. The term collimated comes from the word collimate, which means to make a parallel. Collimated beams are often achieved through the use of lenses or mirrors that help align the light rays to travel in parallel. In an ideal scenario, a perfect collimated beam would not disperse or diverge with distance. However, due to the phenomena of diffraction, it is not possible to achieve a beam with absolutely no spreading. Nonetheless, collimated beams maintain a high degree of parallelism, making them useful in application where minimal spreading is desired, such as layer technology, optical image system, and scientific research. This type of beam is commonly used in various applications such as laser technology, optics, image system, and scientific researches, and also used in industrial applications. Focal point. Light can pass through a lens in either direction. A lens has two focal points, one on each side. Concave lens has two spherical surfaces and therefore it has two principal foci or focal lengths. In case of concave lens, for a concave lens, the parallel rays appear to come from a point behind the lens called principal focus F. However, a concave lens has two spherical surfaces and therefore it has two principal focal points. The second principal focal point is that point where any light ray traveling towards the focal point on the way to the lens will refract through the lens and travel parallel to the principal axis. Optical center. A point on the principal axis at the center of lens is called optical center. It is a point on the principal axis of the lens such that a ray of light passing through this point emerges parallel to its direction of incidence. It is marked by letter O in the figure. The optical center is thus the center of the lens. This is the optical center O. Lens power. The power of a lens is defined as the reciprocal of its focal length in meters, or D is equal to 1/f, where D is the power in diopters and F is the focal length in meters, or the ability of a lens to bend the light falling on it is called the power of lens. Since the lens of shorter focal length will bend the light rays more, will have more power. A convex lens converts the light rays towards the principal axis, whereas a concave lens diverts the light rays away from the principal axis. Formula P is equal to 1/f. Unit, its SI unit is per meter. This is also known as diopter. Focal length. Focal length is the distance between the lens and the focal point where the light rays converge or diverge. It is a critical parameter that determines the image quality and magnification of optical system, including the human eye. Biconcave lens. Introduction. The concept of focal length is a fundamental pillar in optics, helping explain the behavior of light rays and their interaction with optical elements. Focal length is applied in the crafting of lenses in telescopes, cameras, and correct eyewear for individuals with refractive errors. Focal length governs the convergence or divergence of light rays, detecting the precise point where they either converge to form an image or diverge from an image. The vergence of light. The concept of vergence is crucial to understand why lenses refract light and how to determine the focal length. Vergence is an angle at which light rays converge or diverge as they pass through the lens. Converging light has a positive vergence and diverging light has a negative vergence. Vergence is determined by the curvature of the lens surfaces and the refractive index of the material. Diverging or concave lens has a thinner center and thick edges. These lenses cause parallel light rays to spread out or diverge as they pass through the lens. Diverging lens has a virtual focal point from which the divergent rays appear to originate when projected backward, creating an image behind the lens. Light rays that pass through a diverging lens spread out, and when projected backward, they appear to converge at a virtual focal point behind the lens. The focal length of a diverging lens is deemed negative due to this virtual focal point. Focal length calculation. Several equations are used in optics, optometry, and ophthalmology to calculate the focal length. Thin lens equation. One method of determining the focal length of a thin lens in air is the thin lens equation, which relates the Focal length of a lens to the distance between the lens and the object. Focal length is always represented in meters. Lens powers are represented in diopters, and the thin lens equation is given by 1 over f is equal to 1 over object plus 1 over image, in which f is focal length, o is the object distance, and I is the image distance. Compound lens equation. The focal distance of a adjacent lens given by 1 over f is equal to 1 over f1 plus 1 over f2, where in which f is equal to the combined focal length of the adjacent lens, f1 the focal length of the first lens, and f2 is the focal length of the second lens. When two thin lenses are placed a certain distance apart, the focal distance of this compound lens system can be calculated by 1 over f is equal to 1 over f1 plus 1 over f2 minus d over f1 dot f2, in which f is the focal length of the combined lens, f1 is the focal length of the first lens, f2 the focal length of the second lens, and d is the distance between the two lenses. Real and virtual image. Real image. The image in which light rays from one point on the object actually crossed at the location of the image and can be projected onto a screen. A piece of film on the retina of an eye is called a real image. An image that is on the same side of the lens as the object and cannot be projected on a screen is called a virtual image. Image formation by concave lenses. The ray parallel to the principal axis passes through the focal point after refraction by the lens. The ray passes through the optical center, passes straight through the lens and remains undeviated. The ray passes through the focal point, becomes parallel to the principal axis after reflection by the lens. What is lens function? Lens function to recreate an image of an object by refracting the light coming off that object. Lenses refract any light that passes through them at a non-perpendicular angle. The degree of refraction depends on the medium of the lens and the medium through which the light rays travel on either side of the lens, typically air. It also depends on the angle at which the light ray penetrate the lens. The degree of refraction can be calculated with Snell's law. n1 sin theta 1 is equal to n2 sin theta 2, where n represents the refractive index for that medium and theta represents the angle of the incidence. The reason light is refracted is that light levels are at different velocities in different mediums, yet it maintains the same frequency. This phenomena of maintaining the same frequency is why blue light still appear blue, whether traveling through air, water, glass, or any other medium. Applications of concave lenses. Some uses of concave lenses are listed below. Used in telescope. Concave lenses are used in telescope and binoculars to magnifying objects. As a convex lens creates blur and distortion, telescope and binocular manufacturing install concave lenses before are in the eyepiece so that a person can focus more clearly. Eyepiece design. In the eyepiece of a telescope, concave lens may be used as a part of the lens system to further correct aberration, optimize the image, or adjust the eyepiece's field of view. Use of concave lens in peepholes. Peepholes or door viewers are security devices that give a panoramic view if objects outside walls or doors. A concave lens is used to minimize the proportion of the objects and give a wider view of the object or area. Magnification. The concave lens used in peepholes are often designed with the wide field of view. This wide angle view allows for a broader perspective of the area outside the door, enabling better situational awareness. Privacy and security. Peepholes with concave lens provide a way for residents to observe visitors without revealing themselves. This enhances privacy and security by allowing occupants to assess the situation outside before deciding to open the door. Use of concave lens in binoculars and cameras. Aberration correction. In binoculars and cameras, concave lenses are often employed to correct optical aberrations and improve image quality. Concave lenses are used for aberration, reducing distortion. Concave lens can help to reduce distortion. It ensures that the image captured by cameras or seen through binoculars are more accurate and true to life. Improving depth of field. The use of concave lens in the optical design can contribute to improving the depth of field, allowing larger range of distances to appear. This is particularly beneficial in photography where both near and distant objects need to be captured sharply. Use of concave lens in projectors. In projector, concave lenses are employed to spread out light, helping to create a larger and more focused image on the screen. It also reduces distortion and ensures that the projected image remains geometrically accurate. Image size and focus. Concave lens contribute to adjust the size and focus of the object projected image by manipulating the path of light rays. These lenses help project a well-focused image onto the screen with the desired size. Light spreading. Concave lenses are used to spread out light emitted from the projected lamp. This helps in creating a more even and uniform illumination across the entire projection surface, avoiding hotspot and ensures consistent brightness. Light control. Concave lens help to control the direction of light, preventing it from scattering or diverging excessively. This controlled light path contributes to better image contrast and clarity. Use of concave lens in eyeglasses. Concave lenses are used to correct nearsightedness. They help divergent light entering the eye to focus properly on the retina, improving distance vision. An eye care professional can determine the specific prescription needed for your glasses. Defect of vision. Myopia. Myopia is a common vision condition in which near objects appear clear but objects further away look blurry. It occurs when the shape of the image or the shape of certain part of the eye causes light rays to bend inaccurately. Light rays that should be focused on near tissues at the back of the eye retina are focused in front of the retina. Nearsightedness usually develop during childhood and adolescence, and it usually becomes more stable between the age of 20 and 40. Symptoms. Nearsightedness signs or symptoms are included blurry vision when looking at distant objects, the need to squint or partially close the eyelids to see clearly, headache, and eye strain. Main part of eye. Your eye has two parts that focus image. The cornea is the clear dome-shaped front surface of your eye. The lens is a clear structure about the size and shape of an M&M's candy. In order for you to see, light has to pass through the cornea and lens. They bend the light so that the light is focused directly on the nerve tissues at the back of your eye. These tissues translate light into signals sent to the brain, which enables you to perceive image. Causes. The exact cause of myopia is unknown, but there is evidence that both genetic and environmental factors cause myopia. If one or both parents are myopic, their children will also have a higher risk of developing myopia. Children who spend a lot of time in reading, playing games on their mobile devices or doing other intense visual work will also have a high risk of developing myopia. Diagnosis. Glasses or contact lens can correct myopia in children and adults. Laser eye surgery is also used to correct myopia. Allah Hafiz.